We can start if it's okay with you. Okay, so welcome everybody to the webinar of today. The speaker of today is Fabian Denner, and he's going to talk about acoustic emissions of cavitation bubbles and the misleading similarity to acoustic black hole analogues. So as usual, I introduce the speaker and then I give him the floor. So Fabian Denner obtained his PhD from Imperial College London in 2013 on numerical methods for multiphase flows with surface tension, followed by a postdoc at Imperial College. In 2015, Fabian was awarded the prestigious fellowship from the Engineering and Physical Sciences Research Council of the UK, with which he continued his research work on surface tension-driven flows and expanded his research into new areas such as compressible and surfactant laden flows. Since 2018, Fabian has been a junior professor of multiphase flow modeling at Otto von Guericke University of Magdeburg in Germany. His research revolves around developing numerical methods and software tools to predict multiphase flows and applying these methods to answer questions related to the physics and application of such flows. Currently, Fabian's work focuses on interfacial flows with surfactants, viscoelastic flows, multiphase flows in biomedical applications, as well as cavitation and acoustics. So it's with great pleasure that I introduced Fabian Denner for the webinar of today. So Fabian, I stop sharing my screen and you can go ahead and share yours.
All right, you should all be seeing my screen now.
Yes, yes.
Very good. So thank you, Francesco, for the introduction. And of course, thank you to the organizers for inviting me to talk a bit about my work. Francesco already introduced me, so I'll not do that myself anymore. So I've chosen a bit of a topic that has grown close to my heart in the last few years. So some of you might know me, I'm more of a numerical person, but actually cavitation bubbles have also played quite a big role in the last few years because that's quite a challenging application of which I'll show you a bit more about today. And then also I'll talk a bit about something that we encountered in trying to figure out the acoustic emissions of cavitation bubbles, and that is acoustic black hole analogues and why they're not similar to cavitation bubbles, even though some people in the physics community think or believe that. Okay, so first, just to give you a broad overview of what I'm doing, for those of you who are not familiar with my work, my research interests are mainly revolving around, well, numerical methods for incompressible and compressible flows, as of recently also viscoelastic flows. And typically, my work is concerned with multiphase flows, so bubble dynamics and cavitation. You will see more of that today, but also droplets and atomization, a bit of particle-laden flows. And then we want to apply that to something relevant in engineering, let's say. So acoustic cavitation in medical ultrasound, that was originally the motivation for everything I show here today. We've been working on aerosol formation from nonlinear fluid because we also wanted to have something, have our share of the money tree during the COVID pandemic. And also inkjet printing, for instance, for additive manufacturing is one of the interesting topics. I've been working a lot on developing numerical software tools, including a full CFD code, and also worked on some more esoteric topics, for instance, symmetry breaking due to surfactants, as you see here on the right, on a soap bubble, actually. So yeah, it's quite a broad range of topics I've been involved with. Okay, what are we looking at today? So first, I will give you a short introduction, what motivates me, at least, in terms of research in cavitation. I will then look a bit more in detail with you at the acoustic emissions of cavitation bubbles. How can we model them with reduced order models? We will not do full CFD simulations today. And what can we learn about the flow field that actually the bubble oscillation and the acoustic emissions induce? And that will then bring us to acoustic black hole analogues. I'll first explain to you what that actually means or entails. How can we build such a model of an acoustic black hole analog, and why they're not similar to a cavitation bubble. So first, what motivates me about cavitation? Well, it's a key mechanism in many emerging technologies and applications. I mean, that sentence can come straight out of a grant application. Give you a couple of examples. For instance, focused ultrasound is a very important application nowadays. At least there's a lot of research going into it, where we excite microbubbles that are injected intravenously and can, for instance, through radiation forces, microstreaming, or just brute force, when those bubbles collapse, for instance, breach the blood-brain barrier to facilitate targeted drug delivery. So that was the initial application that attracted me. We can have precision cleaning. If a bubble collapses asymmetrically next to a wall, we can generate large shear stresses very precisely on that substrate and potentially clean it. Well, of course, we need to make sure we don't break it in the process. But also, nuclear fusion has recently become a topic of research for bubble dynamics and cavitation. And there is a British company called First Light Fusion, which uses inertial confinement fusion driven by cavitation partly. At least that's what everybody believes they're doing. We don't know it exactly. And they have recently reported that they got actually for a few milliseconds more energy out of their process than they put in. For me, as a person who works on numerical methods, cavitation is very interesting because it's difficult to model. We have a wide range of time and length scales. Cavitation produces extreme conditions, as we will see in a few minutes, which, yeah, makes the modeling assumptions at some point also a bit questionable. It's not feasible to fully resolve a cavitation process because we have thousands, millions, billions of bubbles. And also we don't have much reliable and meaningful experimental data, which means the validation is a bit of a challenge sometimes. So I address this problem in two different ways. First, with classical CFD, meaning a large computer and essentially coming with a sledgehammer to study the complex behavior of a single bubble or few bubbles. That also helps us to further develop numerical methods because it's a very difficult problem to model and to get right as a result as well. And the second part is multi-scale framework. So try to leverage reduced order models to reduced order methods to study single bubbles, but also bubble clusters, the acoustic emissions, the interactions, and that's what I will talk mainly about today. So some of the work, for instance, we have a shock-driven bubble collapse that can be a nice canonical system with which we can test our numerical methods. You see here on the right, you have it's a 2D axisymmetric simulation of a bubble that gets hit by a shock wave that arrives with a Mach number of 1.1. And you can see the bubble now gets involuted here due to the asymmetric collapse. And when this liquid jet impinges on the other side of the interface, we have a multiplication of the incident pressure. We see here on the left in the stationary figure as well, this jet travels at about 700 meters per second, almost 800 meters per second. So we can generate very high pressures. That leads to challenges if we are near to a wall. So we can also have a bubble collapse near a wall, which due to that symmetry generates this jet which pierces through the bubble here with about 250 meters per second. You need to imagine the wall is somewhere down here at the lower edge of the figure, and that may cause damage to nearby objects and surfaces. I presume most of you are familiar with cavitation or have heard of cavitation in the context of damaging objects or propellers, for instance. But it can also be utilized for something useful if we can control it. For instance, for precision cleaning, I already said that. We can generate very large shear stresses here for different dimensional distances of the bubble from the wall. We can easily generate 100,000 Pascal wall shear stresses, and that is, for instance, hypothesized to be the mechanism that helps us open the blood-brain barrier in a very precise manner. Now, today I will talk mainly about fluid dynamics and about reduced order models. So first, let's have a look at the governing fluid dynamics. If we assume that we have a bubble, single bubble, nothing else, that is in spherical symmetry. We have the continuity equation on the left, momentum equation on the right, t denotes time, r is the radial coordinate. So now we can express the velocity by a potential, because our flow is irrotational, and this potential is defined as a function f, I'll come back to that later on, divided by the radius. Okay, we can define the velocity by the gradient of this potential. The minus sign here, it's purely for mathematical convenience. And the function f is now also in itself a function of the retarded time tau. We will get back to that in a few slides, what that actually means in practice. Just bear in mind that's some time associated with the emission. We can then integrate our momentum equation that we see here at the top on the right from r to infinity, so very far away from wherever radial coordinate we are, assuming that in spherical symmetry the potential vanishes at infinity and that the flow is isentropic. Now, this will probably cause a few eyebrows to be raised later on, but just bear with me, we assume the flow is isentropic. Then we have this wonderful equation here. We have the derivative, the temporal derivative of our potential. On the right-hand side, we have the integral of the pressure differential over the density. That is nothing but the static enthalpy difference between the current radial position and the static specific enthalpy very far away from our bubble. Okay, so now we can insert our potential into our transient Bernoulli equation. Here you have the enthalpy difference on the right-hand side again. We can rearrange this now for the time derivative, and we get this function g. Function g is the derivative of function f, and what you get here is in essence the kinematic specific enthalpy difference, so the total enthalpy difference, sorry, times the radius. Okay, and so Kirkwood and Bethe in 1942 then postulated in the context of underwater explosions that G is invariant along a wave characteristic, and that it propagates along this wave characteristic with a certain speed that is the sum of the local speed of sound and the local flow velocity. So then we get this advection equation here along the outgoing characteristic, where any information associated with the wave would travel on or associated with our acoustic emissions. Now that this function g is constant might also look a bit bold, a bit of a bold assumption, but you can simply think of it if we assume that the total enthalpy has to decay with 1 over r, simply due to the geometry of a spherically outwards propagating wave. Then if we multiply this by r, it should be constant. So based on this Kirkwood-Bethe hypothesis, which is quite powerful in simplifying the problem, we can now, we didn't, Gilmore did in 1952, derive the Rayleigh-Placid model. So some of you probably heard about Rayleigh-Placid models, which can be used to model pressure-driven bubble dynamics, so the radial pulsation or oscillation due to changes in pressure. Gilmore extended that to compressible liquids. So the Rayleigh-Placid equation traditionally is for incompressible liquids. Gilmore, based on this Kirkwood-Bethe hypothesis, derived it for compressible fluids. So what you have here is R is the bubble radius, the dots indicate derivatives, time derivatives. C would be the speed of sound of the liquid at the bubble interface. We have the same here for H. H would be the static enthalpy of the liquid at the interface, infinity, far away, and some derivatives here at the end. HL, so the enthalpy at the interface incorporates the boundary conditions such as viscous stresses and surface tension as well. H infinity would incorporate, for instance, if applicable, an external excitation, for instance, an ultrasound excitation, assuming that the wavelength is much longer than the size of the bubble. The gas we assume is adiabatic or compressed adiabatically. That's just for convenience, not a necessity. And we describe the liquid by an equation of state. We need to choose that. In this case, we use the tide equation of state. But anything I show you here is not bound to a specific equation of state. The only assumption is that whatever we do in the liquid is isentropic, or whatever we model in the liquid is isentropic. Good. So now we can model we have a mathematical or numerical framework to model the pulsation or the oscillation of our bubbles. How can we model acoustic emissions? So our bubble oscillates, so the radius changes over time. As a result of this, the pressure changes, we emit waves. How can we simulate that? So from our Gilmore model, we get information, and that information is discrete information at the gas-liquid interface. So we store that, and then we say if we know the velocity with which information should propagate outwards, then we can propagate this information to a future time, right? So that would just be the propagation speed, capital C, times the time step. And then we add new information here, which we can get from our Gilmore model. And if we do this at every time step, then we get this network of points of discrete locations, which we call emission nodes, where we store and our information, transport it, recalculate it. So we call this a Lagrangian wave tracking approach, because essentially you move those emission nodes in a Lagrangian fashion, computationally simple, flexible, fast, easy to implement. Now, the velocity with which those nodes travel, they depend on the local velocity, flow velocity, and the local speed of sound. So it's different for every node, dependent on the position, on the pressure, and other things. So we can have shock waves. So emission nodes with a larger pressure propagate faster and may overtake their forerunning neighbor, which would then lead to a multi-valued solution, which is unphysical. In reality, that would mean a shock would form. We have additional dissipation, generation of entropy, such that multi-valued solutions cannot form. Yes, Rudnick postulated about 70 years ago that it's completely irrelevant where this dissipation comes from. And for those of you who have worked with Euler equations and solving compressible flows with that, we also don't have physical or we don't have dissipation in there in the sense of a heat conduction or molecular viscosity, but still we can simulate shocks. And that's simply because then the numerical dissipation steps in, so it doesn't matter where this dissipation comes from. We take this assumption to an extreme and simply discard the information of the emission node that tries to overtake its forerunning neighbor. And as I'll show you in a few slides, that works surprisingly well. Good, now we need to now we can transport this information. Now we need to compute the information, right? How fast does our emission node travel? What pressure do we have locally? And we go back few decades and use a method proposed originally by Hickling and Plesset, where they solve two ordinary differential equations along the outgoing characteristic. First, we have a differential equation for the radius r, which is the velocity, the propagation velocity. speed of sound locally plus the flow velocity. And we have this little more complicated equation for the derivative, the time derivative of velocity. And again, we have here our old friend, this function g, dependent on the retarded time tau. And then essentially what this retarded time tau means, it's just the time at which this particular piece of information is emitted at the bubble interface. So if I go back, that would be essentially Ti for this node over here, right? So here the information gets emitted. So that's the time tau associated with that emission node. We can integrate this. We use fourth order Ekuta scheme. That's very simple. We can get the invariant. Because it's invariant, it's constant. We can get this from the conditions at the bubble interface, so directly from our Gilmore model. And then also by a bit of manipulation, just rearranging the equation, we can get essentially the enthalpy at any point if we know the related value g, if we know the radial position, what happens in the far field, and the local velocity. So now we have a closed set of equations that we can solve with the Lagrangian wave tracking approach. How does that fare in reality then, if we apply this? The first test case is a Rayleigh collapse. Rayleigh collapse is simply the bubble collapse due to a suddenly applied overpressure in the surrounding. Or likewise, you could also just decrease suddenly the pressure inside the bubble. So there needs to be a pressure difference. Rayleigh studied that over 100 years ago and also derived the characteristic time, the Rayleigh collapse time, as a function of the pressure difference and the density of the liquid. And we compare this to our in-house CFD solver, which uses the volume of fluid method to represent the gas liquid flow. And if we compare them, then that's in wonderful agreement. But in order to get this agreement, so on the left, you see the normalized radius as a function of time. On the right, you see the pressure inside the bubble as a function of time, the average pressure. In order to get this agreement, you can already see the problem with CFD. For such applications, we need 1,000 cells per radius. That's a spherically symmetric simulation, so it's relatively cheap, still very expensive because we need 1,000 cells per radius, per initial radius. We have an extremely small time step, 5 times 10 to the power minus 7, this Rayleigh collapse time. Sorry, that should just be TC and not delta TC. So we have essentially each of the simulations, if you would apply an equidistant time step or constant time step, would be 4 million time steps for a relatively simple simulation. So you can see the motivation why we go to reduced order models. So that works very well. So how do our emissions look? And we now assess the emissions as a function of time, pressure, amplitude, and the velocity at specific locations in the vicinity of the bubble. So here at 3 different points, we can see that both in the top, the pressure amplitude normalized by the ambient pressure, and at the bottom, the velocity normalized by the characteristic collapse velocity. We see that they agree very well. So we're confident that we get some meaningful results. Okay, let's make it a bit more difficult. What if we take a laser-induced cavitation bubble? There, a plasma forms due to the localized energy deposition by a laser pulse. We vaporize the liquid, and the bubble expands, collapses. It's very reproducible in experiments, and therefore also a very good test case to compare numerical methods. Now here we take a reduced order model approach with a modified Gilmore equation that also attempts to model this laser absorption. We model a laser pulse with 265 femtoseconds. First, the bubble dynamics are in very good agreement with the reference results of Liang that were recently published. On the left, we have the bubble radius. In the middle, the velocity of the gas-liquid interface. On the right, the pressure inside the bubble. We can see the bubble here collapses with almost 1,800 meters per second, so that's very violent, generating pressures of significantly above 10 gigapascal. So it gets a bit more violent here. Okay, we can now also go to the emissions. On the left, you see the pressure amplitude of essentially this pressure pulse here that gets emitted when the bubble reaches its minimum radius, so the peak pressure. On the left, the pressure amplitude, on the right, the velocity, the flow velocity that we get from our model as a function of the radial coordinate. We see very good agreement with the work of Liang. Now, there are two specific points here. Well, first, we see the pressure decays rapidly close to the wall, so around here. That indicates shock formation, whereas in the far field, we get a decay that is proportional to 1/r, which we would expect from geometric decay for small amplitude waves. But on the right, we see that the velocity also in the far field decays with 1/r. And that is surprising because what textbooks want us to believe is that the velocity should decay with 1/r squared, because that's what we see in an incompressible liquid. Well, we see, and Liang obviously also saw something different, we see a 1/r decay. So that's something we will have a bit closer look. We can go to a third case, so lipid-coated microbubble, which is used as contrast agent in medical applications, as a contrast agent to enhance contrast, but also recently to facilitate therapeutic treatments. The bubble in this case is 1 micrometer. Initial radius is filled with sulfur hexafluoride, which is very heavy, therefore doesn't dissolve easily in liquid, in the water. The lipid coating further stabilizes the bubble against dissolution. We apply 1 megahertz excitation frequency and an excitation amplitude of 600 kilopascal, which is representative of high-intensity focused ultrasound therapies. On the left, we see the radius as a function of time. In the middle, the Mach number of the gas-liquid interface, and on the right, the liquid pressure directly at the gas-liquid interface. Okay, we see periodic oscillations of the bubble. Mach number of about 0.5, so compressibility definitely is important here. And on the right, we see again gigapascal pressures that are generated in the liquid. We can again look at the emissions. So same plot as before, we have delta P, the pressure amplitude as a function of the radial distance and the velocity. And essentially we see almost the same scenario as for the laser-induced bubble. We have a rapid decay with shock formation, geometric decay in the far field of the pressure, and on the right for the velocity initially accelerates and then decays with 1/r. So again, it's intriguing why this is the case. We can also look at individual profiles of the pressure. So we see exactly the same picture as before. Looks familiar compared to the laser-induced bubble. We have a geometric decay for the pressure in the far field, and for the velocity, we have a 1/r decay as well. Okay, so now we can look at the wave profiles as well. What we have here is essentially the pressure profiles and the velocity profiles as a function of the radial coordinate at different time instants. So T naught would be the time at which the maximum pressure would be emitted. You see that here on the left. And then we see this rapid decay at the beginning as a result of the shock that forms here, which we can see very nicely. It then sort of mellows out. But what we can also see is this extreme velocity difference here. So the shock front coincides with a change of direction of the flow as well. So basically, the change in direction is communicated to this flow that is accelerated during the bubble collapse by this outgoing pressure wave. And that leads to rather extreme accelerations. For this case, for instance, it was of the order of 10 to the power 14 g, where g would be the gravitational acceleration. So quite violent. So that tells us a bit about the flow field, but we might want to have a bit of a closer look at this. And with what we see here, the insight is limited. So the employed ODE that we solve to get the velocity does not allow a detailed analysis of the flow. And especially we would like to know what is basically a flow induced by the displacement of the liquid due to the motion of the gas-liquid interface, and what is acoustically induced. So if we go back, we have our velocity potential with our retarded time, and at any given point in time, we can basically calculate this retarded time if we integrate the velocity backwards in time that we had till to the time at which the information was emitted at the bubble wall. And we insert this into the definition of our velocity in relation to the potential. Then we get this explicit expression for the velocity at any point r, so at any radial coordinate. So again, we see this function g. We have the speed of sound and the velocity, the flow velocity, but also we have the second term here, which is f, which was part of the potential, which is the antiderivative of g, that decays with 1 over r squared. And in fact, this first term represents the hydrodynamic contribution, and as hydrodynamic contribution, I mean the contribution from as a result of the displacement of the liquid due to the bubble, the gas-liquid interface motion. The second part is the acoustic contribution. And you can simply, if you would assume an infinite speed of sound, so you have a perfectly incompressible liquid, then you would again only get the contributions that you can also derive from incompressible liquid based on the momentum equations. So now we have a means to separate those two contributions, hydrodynamic and acoustic. And Prosperetti in 1984 postulated that the hydrodynamics should dominate the near field, the acoustics dominate the far field. So we can put this hypothesis or this analysis to a test. F, we assume also that it's an invariant that we can define at a bubble interface based on the results of our Gilmore model. So again, we get a closed set of equations. We compare this, how for our lipid-coated microbubble, we see that it doesn't matter whether we define the velocity based on the ODE or compute it based on the ODE, that would be the blue line again, or if we compute it based on this explicit expression for this particular case. I mean, this explicit expression has its limits, but for this particular case, we get a satisfactory agreement, both for the pressure amplitude as well as for the flow velocity that we predict. Okay, so now we have this new formulation. What can we do with it? So the first question is, well, if one term scales with 1 over r squared, the other term scales with 1 over r, well, where is the transition? So where do basically the hydrodynamics hand over the dominance to the acoustics? So we can take those two contributions, set them equal, evaluate everything for simplicity at the gas-liquid interface, and then they're equal for what I call this hydrodynamic acoustic transition radius. Okay, so that we can define a priori, or rather based on F and G and the conditions at the interface. And okay, now we can plot this for different time instances. I picked a very nice example out here. So that's where the bubble interface or the bubble expands at maximum rates with maximum velocity. In black, you have the velocity of the flow. In blue and red, the two contributions, hydrodynamic and acoustic. And we can see first we have the hydrodynamic contribution that dominates, and then the acoustic contribution. And approximately at our transition radius, they indeed cross each other. So in the far field, the acoustics are dominant. That's very nice. What can we do with that? We can plot this now in a space-time diagram. So we have here one oscillation period of our bubble. On the x-axis, we have dimensionless time. On the y-axis, we have the radial coordinate. Everything that is white is inside the bubble. The thick line is the gas-liquid interface. Everything that's red is acoustically dominated. What's blue is hydrodynamically dominated. So we see that, okay, if we take this approximate boundary separating the two regimes, the hydrodynamics are dominated in the near field. In the far field, it's the acoustics that dominate, aside from this extreme values or those limits that we have here. Now, if we zoom in to the interesting part, where the peak pressure is emitted, that would be here at the minimum radius. If we zoom in, and that's just 4 nanoseconds that we show here, we see that actually the acoustics or the pressure peak is emitted in the purely acoustic regime. So that's why we see, or the pressure peak just sees 1/r the whole time, or rather the velocity associated with it. It's just in the acoustic regime, and that seems to explain why there is a slower velocity decay than expected based on geometry. It's purely the particle velocity of the acoustic wave that dominates here. So we've learned a few things about the flow field now. What we rather would learn about actually is the acoustics, because if we have a medical procedure, for instance, or if we want to clean ultrasonically with cavitation, what's typically done is the signal is recorded. So a hydrophone is used, for instance, signal is recorded, we do an FFT and get a spectrum back. And that spectrum for this lipid-coated bubble looks like that. Well, we have a lot of peaks. So what you see here is at different locations, what the spectrum looks like, normalized here with respect to the bubble radius of this lipid-coated bubble. On the x-axis, logarithmically, the frequency relative to the excitation frequency. We see, okay, the first harmonic is obviously dominant, the second harmonic, and so on. Higher harmonics at some point get damped out. That's also expected, but we don't really understand where those peaks are coming from. And that would be really the holy grail of this kind of acoustics. The problem is that it's a very mixed bag in terms of contributions. We have the cumulative nonlinearity that would be responsible for shock formation that we saw. We have local nonlinearities due to the curvature of the wavefront. We have very small bubbles, so the curvature is important. We have primary frequency modulation as one of the Doppler shifts, which I'm sure you're all familiar with from the ambulance driving past. And we have also amplitude modulations and secondary frequency modulations that are associated with that in an accelerating flow field. And so our question is, how can we untangle all those contributions? It's difficult in experiments. Well, maybe we can do that with a bit of clever math and some good numerics. So that's our motivation. That then sort of brought us to acoustic black hole analogues, which I appreciate is a very exotic topic, but it's actually a very nice model system we found. So if we look at a spherical emitter, and a bubble is essentially a spherical emitter that emits the same frequency as it oscillates with. Now here we have a spherical emitter, the radius on the x-axis, time on the y-axis, and this emitter emits acoustic waves at a higher frequency than it oscillates with. That's the main difference here to the bubble. And it collapses with a velocity larger than the speed of sound. You can see here the characteristic in this dashed lines. The red and blue is the amplitude of the potential that is associated with the emitted acoustic waves. And the thick black line here would be a sonic horizon. So basically, that forms when the emitter collapses with a velocity faster than the speed of sound. And then you can see whatever is emitted within this acoustic horizon can't leave the acoustic horizon because, well, it doesn't travel fast enough to breach that horizon. It's essentially an event horizon for acoustic waves. So they can't leave. Similar as in a black hole, we can't leave. So we have a temporal acoustic black hole. And that's sort of what sparked our interest. And what we also see, if you look at the amplitude, so at the colors here, we see that we have an amplitude modulation. So either the amplitude decreases when the emitter expands, or the amplitude increases when the emitter collapses. So we have an amplitude modulation that we see here, at least in the potential. So what are acoustic black holes? So there are two very prominent examples in reality. First is a stationary de Laval nozzle flow. Most of you are engineers, I presume, so you're familiar with the de Laval nozzle. We have a converging, diverging nozzle, we accelerate, and at the throat we have a transition, a sonic transition to supersonic flow. But that means everything that is emitted in the diverging part of the nozzle, any sound waves can never reach the converging part of the nozzle. So that's an acoustic black hole in 1D essentially. Also, so-called Bondi-Parker type flows, which are, for instance, solar winds or the mass accretion of black holes would satisfy such a condition. And those Bondi-Parker flows is also what we use as a model system here. I'll come back to those two later, because what they both assume and what we assume in our acoustic black hole is a shock-free transition from subsonic to supersonic flow, which in itself is a questionable proposition, let's say. Okay, so far acoustic black holes have mainly been studied towards analogues for gravitational black holes. That's because we can make an analogy to curved space-time, and it allows to study, for instance, Hawking radiation in a non-relativistic system in a lab. And Fisher, one of the pioneers on acoustic black hole analogues, he postulated in '98 that a cavitation bubble might be a nice example that can be experimentally realized of such an acoustic black hole, simply because, we go back, if this would be our bubble of our gas-liquid interface, we can easily generate a bubble that collapses with supersonic speeds. Well, then we can generate temporarily an acoustic black hole. I'll show you later why that's not possible. So we take a canonical acoustic black hole. That's our model system. Our flow basically converges towards this singularity in the middle. We have spherical symmetric flow. We have this emitter that emits waves at a certain frequency. And as the color gradient indicates, the velocity increases towards the center. That's simply due to energy conservation. We will have to increase the velocity as we go further in. So at some point we have this sonic horizon where the flow transitions shock-free from subsonic to supersonic. So the question is, okay, how can we model this? What can we get out of this? Especially what we are interested in is Doppler effects, and how can we separate what comes from a non-uniform flow field and what comes from essentially a relative motion between flow and emitter, or between the bulk flow and the emitter. So can we somehow separate them? Because the second point has been studied quite a bit in recent years. And we have an acceleration. That's nice, and a well-defined acceleration. So again, we take a velocity potential, this time a positive, not a negative one. That's again just for convenience. We have a continuity equation and a Bernoulli equation. On the right-hand side, we now also have a gravitational potential. That's different than before. And we take a perturbation approach. So subscript 0 always indicates basic background flow quantities. And then we have a small parameter epsilon, and the acoustic contribution defined as with subscript 1. We can derive a wave equation. We didn't come up with that idea. That was Unruh in '81 who did that. We can define this wave equation, and the nice thing is we can rewrite this with a metric tensor that we can use to define a space-time. And that will then be analog to a curved space-time for gravitational black hole, for instance. And essentially what we get is a space-time diagram that looks like that. We have space on the x-axis, time on the y-axis, a singularity in the middle, and our acoustic horizon. Everything that gets emitted on the left, so inside the acoustic horizon, eventually falls into our singularity or into our black hole. Everything that is emitted on the right propagates outwards We've already been familiar with that. And at some point, if the curvature of our wavefront becomes small enough, we essentially have a plane wave again. That's what we want to achieve here. So now we define a stationary background flow based on our emitter velocity and the radius of the emitter and exponent n. If we would use exponent n equals 2, we would have an incompressible flow. We can choose any n. We can be varying. You can incorporate the density changes of a compressible flow. We can even simulate a flow in any 1D flow, even in the Laval nozzle, for instance. We then have a surface gravity, which is called surface gravity in analogy to what a free-falling observer at the event horizon of a black hole would experience. Essentially, it's our flow acceleration at the sonic horizon. Again, defined here on this exponent n, the speed of sound and the radius of our sonic horizon. And we can define a Helmholtz number that puts the geometry or the size of this black hole in relation to the emitted wavelength. We can rearrange those two equations and define a modified Helmholtz number that only depends on the background flow acceleration and the emitted wavelength, and the applicability is not restricted to spherical flows, so to any 1D flow. So we basically got rid of the geometry in our Helmholtz number. Good, what can we do with that? So if we look at the space-time diagram of a spherical acoustic black hole, we get those, okay, our black hole, our emitter starts collapsing here where my cursor is, and then collapses into this black hole at an increasing velocity that is predefined. At some point, we have the sonic transition, which then gives us a plane linear standing wave in the proximity of the sonic horizon, which we can use as a fixed observer. And that's the convenience of this modeling approach. And we can see those diverging characteristics here away from the sonic horizon. And that's exactly what we earlier hypothesized in our space-time diagram. If we apply this now, and I could go on for a long time about this, I just want to show you one result, and that's the geometric similarity. So if we have a specific Helmholtz number, we can, for instance, change the acceleration. That would be acceleration values. If I remember correctly, that would be, I think, similar to what we get at the black hole in the center of the Milky Way, something like that. I need to ask my postdoc again. But if we change this acceleration values, we get geometrically similar wave characteristics. So we have some sort of geometric similarity. However, the amplitude changes. And what's interesting here is that indeed the amplitude of our potential, of our wave potential, increases as it propagates outwards and doesn't monotonically decrease as we would expect from our 1/r decay, or just based on the geometry of our system. We're still not fully understanding this. We're currently investigating this further, but it's definitely an interesting model system to study. The last thing I want to show you is why a bubble cannot be an acoustic black hole analog. So I showed you the De Laval nozzle and the Bondi-Parker flows as the two systems we can observe, two acoustic black hole analogs we can easily observe. And if we take the continuity into momentum equations, if we have a De Laval nozzle, just replace r by the streamwise coordinate in this case. We have the continuity into momentum equations. If we put the continuity equation, rearrange it, put it into the momentum equation, we can get the derivative of the velocity along the primary coordinate axis. You see here in the denominator, this equation is singular when we are at the sonic transition, which is typically indication of a shock front. So we can only circumvent this, this shock and have a shock-free transition from subsonic to supersonic flows if everything in the parenthesis cancels. So if that's 0, what's in the parenthesis? And we know that the sonic transition in the Laval nozzle is shock-free, and we can observe with a telescope that in Bondi-Parker flows, that's true too. So why is that the case? In a de Laval nozzle, it's simply because in the throat, the area doesn't, the cross-sectional area of our nozzle doesn't change anymore along the governing coordinate, and our gravitational potential is, the gradient of it is roughly 0. So everything in the parentheses is 0. The Bondi-Parker type flows, and that's what defines them as Bondi-Parker type flows, we actually have the change in area that the flow flows through the cross-sectional area is balanced by the change in gravitational potential. So a bubble cannot be an acoustic black hole because one, our area always, the area changes with respect to the radial coordinate with 2 over r, but the gravitational potential is roughly 0, or the gradient of it. Secondly, any small deviation from spherical symmetry would result in shock formation. We can see that in Bondi-Parker type flows. And that would mean that we would have to avoid perturbations at any cost, and that would require superfluid conditions. Otherwise, we get simply perturbations due to Brownian motion. So a bubble cannot be an acoustic black hole. Okay, I hope I didn't run too much over time. Despite my technical issues, let me conclude quickly. So I hope I was able to convince you that a bubble collapse can generate very extreme conditions. So we have high pressures, high velocity, large velocity jumps, large accelerations. Our thermodynamic assumptions, I didn't say much about that, but they may become a bit questionable. We have done some work on that as well. But also all the results I showed in terms of cavitation, you can reproduce. We've written a small software tool in C, lightning fast, very easy to use, which you can play with or reproduce the results. Emerging technologies, however, require very detailed understanding of the emissions, and I think we're not there yet. Cavitation monitoring is very dependent on that, especially in medical treatments. But also if we want to avoid material damage and erosion, if we use cavitation-driven cleaning, which has a lot of advantages because we don't need, for instance, any sort of detergent to clean. We can do that purely with fluid dynamics. The acoustic black hole provides, I think, a very nice model system to study nonlinear acoustics. So our aim is to study nonlinear Doppler modulations in isolation. We have a very well-defined observation point at the sonic horizon. And if you want to know more about that, we've recently published a paper on this as well. And of course, I didn't do all this work myself. I had 4 very talented master students helping me with this over the last few years. Postdoc working with me, Sören Schenke, who has done a large part of the work I presented today. My colleagues, Fabian Severin, Roberto González Avila, and Fabian Reuter as well, who have supported me in that. And also my colleagues, Bernd von Bachem and Klaus Dieter Ohl. And last but not least, that would have not been possible without the generous funding from the German Research Foundation. And I hope you had an interesting hour with me, and of course I'm available for questions.
So thank you, Fabian, for the very detailed and very interesting presentation. So I would just say let's open the floor for questions. So whoever wants to ask a question, just feel free to unmute your mic and ask your question. You can also write in the chat, by the way, and I can report the question eventually.
I guess everything was clear.
So, well, then I can myself ask a question. Actually, there is a first question which I would like to ask on the model you presented for acoustic black holes.
Yeah.
In this, what would be eventually in this kind of when we would like, if we would like to apply this modeling as approach to interpretation of an experiment, are there other hypotheses that are kind of broken when we consider actual experiments with cavitating bubbles, or there are actual cavitating bubbles which can somehow tend to this model?
Yes, I think the biggest assumption in all of this, when we go to cavitation bubbles, aside from, I mean, you can imagine we have these extreme velocities, so temporarily you would even have an acceleration that would be comparable to the gravitational or the change in gravitational potential that would balance the change in area. But the problem is that in experiments, it's almost impossible to get a spherically symmetric bubble, especially if you have a very strong collapse. You have small parametric instabilities that grow exponentially. There are experiments on sonoluminescence, which are repeatable and which seem to observe spherical symmetry, but then you would still need avoid any sort of perturbations to get around the shock formation at some point.
Well, okay, so it's really like...
So I think for bubbles, it's, I mean, I say here, it's very strong wording as well, cannot be an acoustic black hole. I think in the abstract, I formulated it a bit more carefully, it's unlikely.
Okay. Okay.
It's just, that's how we got to it. I mean, we were studying, we tried to figure out the acoustic emissions of a moving, just a moving emitter. So emitter moves, accelerates, and that's how we somehow stumbled over this acoustic black hole, also in relation, because there is this notion that a bubble can be an acoustic black hole. That's why we jumped on this and thought, oh, this is very interesting. Yeah. Okay. That's why I thought I'd throw this in here as well. Okay.
And actually, I had another question that's more like very classical on bubble formation. I mean, there are like several ways to form cavitating bubbles, and but then I mean, how does the dynamics of the bubble depend on how the bubble has been formed, either by laser focusing or by, is there some
That's a very good question, especially I think especially for laser-induced cavitation, for instance, because what we model, and also if we do that with CFD, where we had some success modeling, and I see at least 2 people in the audience who did a lot of work on that as well. We neglect a lot of the physics and still get it right in the numerics.
Yeah.
So essentially, as far as I understand it, it's mainly an inertia-driven phenomenon. So if in laser-induced cavitation, you have this whole plasma formation, laser absorption, plasma formation, and so on. In a CFD simulation, we just initialize a small bubble with an overpressure and fix that overpressure, or tune that overpressure so that we get the same maximum radius, and all of a sudden everything else falls into place, which tells you it's inertia driven, because mass transfer and so on seems to have not that much of an influence. I mean, it has an influence, but you can get away without modeling mass transfer, for instance.
Yeah, I just was asking it because, I mean, the theory includes like the thermodynamic theory includes the enthalpic term, and that somehow that's the place which would.
I mean, here what we model with the enthalpy again is crudely an isentropic static enthalpy, static specific enthalpy. So again, there is I tried to find a slide. It's again a very strong relatively strong simplification.
Mm-hmm. Okay.
Anyway, it doesn't matter. Yeah, here we just have H is a function of pressure and density. And what I didn't say is, okay, you have polytropic exponent
As a polytropic, yes.
here, and some pressure constant B, which is a model constant at the end of the day.
Yes. Yeah. That's basically it's what is supposed to be valid after the bubble has been formed and reached a kind of thing. It's like
yes,
kind of that's the hypothesis.
That's the way of putting it.
Okay, I see that there is a question from Robert Metin. So go ahead, please.
Yeah. Hello, can you hear me?
Yes, hi Robert.
So hi, I'm Robert from Göttingen. Thank you very much for the very nice presentation. I have a question. I didn't quite get the how you truncate the shockwave point. So when you have the overtaking points, like here, yes.
Yes. So let's assume this point overtakes that point. Yeah. Then the point that wants to overtake gets deleted. That information goes away.
And that's all you do.
That's all we do. I know it at the beginning. It was basically, we just played around and it worked. So that's really all we do. And interestingly, I looked at the book of Cole on underwater explosions from the 1948, I think, when I prepared this presentation, because I had a discussion with postdoc working on this as well. And actually, Cole already explains a very similar analogy, a very similar mechanism where certain information really just gets lost on the way or dissipated away. And if you read that, it almost reads like the explanation we put ourselves, or we came up with when we designed this. So essentially, the information gets dissipated and we just throw it away. That's really all we do. Although I should say that would mean that ultimately there might be a smarter way or better way of doing it.
What other people did is then to take the double-valued function and make a vertical line where the same area, no?
Yes, the reason why we didn't want to do that, exactly as you say, so they run it, they have the multi-valued solution, and then in a post-processing step, as far as I understand, they apply the equal area rule or whatever it's called, and then you can also get this right, possibly better than what we do, because we tend to over-predict the dissipation.
That was the main question. So are you have you compared to other methods?
That's exactly, I didn't say it, but that's what Vogel and Liang did. They do exactly that with the laser-induced cavitation. They have a similar modeling approach. They don't have this Lagrangian wave tracking. They basically simulate or integrate the solution at constant time intervals. And then afterwards, they remove the multi-valued solutions, and then they get those dots here.
Okay,
that's why I say I think we're over-predicting it a bit.
Okay. Yeah.
The thing is, the motivation why we didn't want to do that, I should explain a bit more maybe, is because what we're interested in ultimately is plugging that or combining that with our CFD code and do bubble interactions. And so we want to, our motivation was to resolve the shocks on the fly, essentially, during the simulation, not be contingent on or reliant on a post-processing step.
Okay, yeah, interesting, great.
It's also interesting that it works despite being so crude.
Yeah, therefore it would be good to have a good characterization what you really do, and where the limits might be. I don't know.
Yes, I mean the code is open source. I can point you to the line where we really just delete this information.
Yes, I believe it. That's a black hole in your code somehow.
Yes, I mean, Rudnick said it doesn't matter where the dissipation comes from. We put it to a test.
Okay, thank you.
Okay, so let's see if there is someone else. Please, Max, go ahead.
Hello, do you hear me?
Yes, hi Max.
Hello, Fabian. I'm actually a bit new to acoustic black holes, so I ask myself, what does it physically mean if there would be an acoustic black hole? Would that mean that information is dissipated? And so I'm thinking in terms of experiments. What could we see then if there was?
Well, essentially, I think the simplest version of an acoustic black hole is a Laval nozzle, because anything that gets emitted in the diverging part of the nozzle can never reach the other side of the nozzle, can never reach the converging part, simply because it's not fast enough. It doesn't propagate fast enough. So it's essentially trapped. You can see it here as well. Those characteristics of this information, of this wave particle, let's say, that gets emitted here, it cannot basically leave the acoustic horizon until the flow turns subsonic again, or the horizon disappears. It's basically trapped because it can only move, let's say, with the speed of sound outwards, but the flow coming the other way is faster than the speed of sound, so it gets dragged away from the sonic horizon. As far as the acoustic wave is concerned, it's an event horizon. It can't see what's on the other side. It cannot reach the other side. It would be as if you would be traveling faster than the speed of light. You can also never reach that side of the diagram. If you would put it in a 2D diagram, in a space-time diagram.
I think Max wants to know what would you observe with a black hole bubble, or how would you detect it, or what would you expect to see?
That's probably more a question you can answer. The two of you can answer. You do the experiments. To be honest, I'm not completely sure. I mean, we've looked at this for a year now, and there's still a lot of open questions. How that would be realizable, how can we exploit this as well? We just saw that people exploited the other way around. There were experiments where they were measuring Hawking radiation or super radiance and things like that. We're not interested in that. We want to apply it the other way around. But I mean, I'm happy to hear your opinion on that.
Well, I think the bubble would be quiet in some moment, so we wouldn't have outgoing sound from the bubble.
Yes, the emitted stuff. But the thing is, the bubble, which is also different than what we see here, the bubble emits at the same frequency as it oscillates with. So if you would assume that the bubble collapses here, it doesn't emit much here. Well, what it emits cannot leave at that point, this sonic horizon, but at some point, it will be able to leave because the bubble would oscillate in the other way again, and the peak pressure would be emitted at the minimum radius, but at that point the velocity of the gas-liquid interface is zero.
I have another question to this. Is in the bubble collapse, the sound speed near the bubble changes, of course, because the pressure piles up already during collapse. Yes. Is a bubble wall speed really passing the sound speed in the liquid next to it?
It can. So in this, it can. I mean, at least our code would predict that. You can come up with easily with parameters that would mean that the collapse is not Mach number 0.5, but 1.2, let's say, or 1.5. And actually, in this example of the laser-induced cavitation bubble, I think the Mach number, if I remember correctly, is about 0.95 or something like that. It's very close to Mach 1. And that's trimmed by Liang towards an experiment conducted as well.
Okay, but that's taken into account, yeah? That,
So it can be possible. I think it is feasible that it collapses with a supersonic speed. How you would measure that, or if you can measure that, different question.
Okay, thanks.
That's what I was saying earlier, that validation is not that easy.
And just as a follow-up question, is there any sort of any model that's kind of takes into account the interaction of two collapsing bubbles at supersonic bubble?
It's a good question. Well, there's a lot of issues with that. I think maybe we can learn something from, I'm sure we can learn something from that, but if we observe that in reality, it's a different question, because those bubbles will almost certainly not be stable.
Yeah.
And
yeah, because I mean that's somehow kind of a point where this theory is supposed to somehow kind of move away from the analogy with black holes, because I mean the horizon is not supposed to behave, the merging of the two horizons, one for light, one for sound, is not supposed to behave the same way, I suppose.
Yeah.
I believe that's speculation, but I believe that's the case, right?
Yeah.
And maybe like having multiple bubble collapsing at supersonic speed can kind of create a sort of sound barrier sort of thing.
Okay. I haven't thought about that. Interesting suggestion. But the question is, in reality, would they collapse? They won't collapse spherically anymore. So they would collapse with a reduced rate, so with lower velocity, lower peak pressure, etc. Well, yeah, okay. I'll need to think about that.
Okay, so I see. Max, just feel free to unmute your mic. Go ahead, ask a question.
Yes, so I just had the idea, as far as I understand, you can produce a pressure signal that a hydrophone would measure for a superspherical bubble. And if the superspherical bubble would be superspherical, you said it could have, or it could be a black hole, no? Because superspherical...
Temporarily supersonic, yeah. It would collapse with supersonic speed temporarily. Well, the thing is, first of all, is the transition shock-free? That would be an interesting question to measure, or I don't know if that's measurable in any way. And the second, then, yeah, temporarily, that could be possibly an acoustic black hole. I don't think it would lead to much, to be honest, because it sort of emits something continuously, not at a much higher frequency than it collapses with. So I don't know what you would expect from that, to be honest. That's something we could actually test in numerical simulations as well, I think. What sort of comes out at the end?
Yeah.
In principle, our numerical framework can also work, I mean, should also still work if the bubble collapses at supersonic velocities. Of course, then the question is, what happens at the singularity? Because the denominator becomes zero, or goes to zero at Mach 1. I haven't tried it. I mean, I've run it, and it can do supersonic flow speeds, but I haven't looked at it in detail and analyzed it.
Okay, so the question should maybe boil down to, can we measure, or can we see from a hydrophone measurement whether
should we expect that we can see it in a hydrophone measurement?
Yes. If there was.
But then your hydrophone needs to have a very high frequency as well. Right, if you want to measure anything in that respect, because your hydrophone would have to, I mean, the collapse is extremely fast. So we'd have to resolve that time interval where the bubble collapses at a very high speed. I'm not sure what a common microphone can, hydrophone can do. Yeah.
Okay.
I haven't worked so far with hydrophones, so
Okay.
I cannot tell. Sorry. Well, thanks.
Okay. So I would say let's just go ahead with the last question. So Alan, go ahead.
This discussion of hydrophone brought a thought to mind. One difference from gravitational black holes is there is a signal that can propagate faster than any of the speeds we're talking about, and that's the speed of light. In other words, optical observation of what's going on inside the bubble. Now, there are such things as these pressure-sensitive paints, indicating that at least there's a possibility of having an additive of a molecule within the fluid that somehow could have a fluorescence characteristic that would tell you the local pressure, and then have some laser activation or something, and then you can get an electromagnetic signal out. Now, these length scales and time scales are so small, you might need a very high frequency signal, maybe ultraviolet or X-rays or something, but I don't know if that's been explored at all.
That sounds like a very interesting suggestion. To be honest, I don't know. I'm not an experimental person, and I didn't stumble over anybody having done something like that. But I don't know if that's realizable in practice. But if it would be, that would definitely be a very, very powerful way of, well, first of all, determining does this make sense what we see here, or what we predict. Very nice, thanks.
Okay, thank you.
Interesting.
Okay, so I think we can well, first of all, thank you very much for the presentation of today. That, as you could see, it was animating a very intensive discussion. And
well, thank you for inviting me. And on behalf of my laptop, I want to apologize for the quick interruption, or for a short interruption.
oh, no worries. That's technical problems that are kind of it can always happen. Don't worry at all. And but thank you very much for this talk. And I also invite the participants to thank you once again, and for staying for so long to reply to questions. And thank you.
Thank you as well.
Good evening.
All right. And well, happy Christmas if I don't see any of you again.
Happy Christmas. Bye.
All right. Bye-bye.
Bye.
Bye-bye.